So hi everyone. So in this video we are going to discuss about case study regarding car steering become unstable in a control system because normally every car is having some stability in their control. Suppose if the car is going to become a brake failure or some problems around in this car means, then what will we have to monitor, and these things we are going to analyze and in this video. So normally the car is having three type of system we need to check. First one is accuracy of the system and speed, accuracy, stability, and acceleration. So based on this, the car will be accessed and it is going to be a proper way. So if it is having any problem around this, we need to check this system. It is having a type 0, type 1 and type 2 system. And moreover, these systems will be identified in PID controllers, proportional, integral and derivative controllers. So these controllers are very useful to identify the problems which is occurred in the car, and moreover it will provide a solution to the car to which path it will going to be check it will be moved towards the final one. So let me see how this stability analysis has been occurred and it can be rectified in the car.
So first let's understand the statement. So what we are going to see is the steering instability at high speeds. The cars mostly become unstable when at high speeds, and this could be caused due to various reasons. It could become unresponsive, slow to respond, or we will lose general control of the car. So to understand and fix this issue, we need to know about a key concept called damping ratio. The damping ratio means that it is the ratio of actual damping coefficient and the critical damping coefficient. To put it simply, it is the time it takes to come to the steady state after a disturbance. So to know this, the damping ratio is denoted by the letter zeta. So when the damping ratio is greater than 1, it is called the overdamped. So what happens here is the system becomes it oscillates more. The system oscillates more before it comes to the stability. And then there's the other thing called the critical damping. This is the ideal damping system that everything should have. It is where the car will be stable and it will come back quickly. It will stabilize quickly. And then we've got the underdamped system. It is when the damping ratio is less than 1. Sorry, overdamped system is when the damping ratio is greater than 1. It is when the damping ratio will be greater than 1 and then the car will be stable but slow to respond. So this is where what we got to know, and this can be rectified by analyzing the sensors and by tuning the algorithms, and also by testing these at different speeds. So the other things will be explained by me.
Analyze the current control system to identify the components. The smart car steering system. The components are servo motor, feedback sensors, controllers, and actuators. Feedback sensor examples: steering angle motors can detect the car steering control position. Control process the feedback and achieve the steering position of the angle. Then to determine the analysis of instability, low damping, it might cause at high speed, if there is insufficient damping in the system, it might lead to oscillation. Improper turning of controller, the control parameter such as in gain in a PID controller can cause the instability. System delay and in the system cause electronic and sensors can cause instability.
So guys, I'm going to talk about the stability response analysis. There are 4 types of stability analysis. And the first one is frequency response analysis, and it's about using Bode plots diagrams to determine the system frequency is response to the higher frequency response with higher speeds. Then the system is the higher speed gain might be indicated as the instability of the system. And second one is about root locus of the system. plot the root locus of the system. Then to determine the poles of the system is moving to right side of the complex plane, then the system might be indicated as a unstable form. And the third one is about Ruth-Wordsworth criterion, and it's about using a body plot understanding to determine the system is using a system characteristic equation. The system is stable or not is analyzed.
If it is positive, then it is stable.
Yes.
Or negative, it is unstable.
At last, the Nyquist equation. The Nyquist equation is analyzing the open loop transfer function by open loop transfer function. If the insertments of the range of -1, 1 and 0, if the range is fixed to it, and it helps to determine the system is stable or not. So these are the stability response techniques.
Okay, next one we are going to see about improvement of the stability. Turning of the controller, adjust the PID controller. Okay, in that we are going to see about some points. First point is about reduce the proportional gain if the value is overshooted, and second one is improvement the initial value of the PID control for the overshooting the control. Third one we are going to see about the PID controller sensors, where it uses sensors for sensing the device, which is used for the programs. Then we are going to see about the enhanced damping. Enhanced damping in where we set steering
Seeing the values of it and some inputs.
Enhanced damping is used to reduce the overshooting of the PID control.
The next part of model-based controllers. Apply the model-based controller is to separate and compensate for speed related system changes. Use state for space control, no control adjustments. Integrated feed forward controls due to the anticipated changes to the steering demand. Use these techniques for reduce the instability and especially to high speeds.
So in this video, we have discussed about overshoot techniques and stability analysis methods and PID controllers. We have discussed about all those parameters which is to be analyzed in the car functions. Thank you.